and that it would stay there. That's the whole idea. Namely, that the voltage divided by the current remains a constant. However, what you're going to see is like this. Current goes up, but then the resistance goes down. Then the resistance goes up. When the current goes up, the resistance goes up. And then, therefore, the current will go down and will level off at a level which is substantially below this. So you're looking there, you're staring at the breakdown of Ohm's law. And so that's what I want to show you now. So here we need 125 volts. And there's the light bulb. And when I throw this switch, you will see the pattern of the current versus time. You only see it once, and then we freeze it with the oscilloscope. I'll turn this off. So look closely now. There it is. Forget this little ripple that you see on it. It has to do with the way that we produced 125 volts. And so you see here horizontally time, the time between two adjacent vertical lines, is 20 milliseconds. And so indeed, very early on, the current surged to a very high value, and then the filament heats up, and so the resistance goes up, the light bulb, and the current just goes back again. From the far left to the far right on the screen is about 200 milliseconds. That's about 0.2 of a second. And here you get a current level which is way lower than what you get there. That's a breakdown of Ohm's law. It is actually very nice that resistances go up with light bulbs when the temperature goes up. Because suppose it were the other way around. Suppose you turn on a light bulb and the resistance would go down. Light bulb gets hot, resistance goes down. That means the current goes up. Instead of down, the current goes up. That means it gets hotter. That means the resistance goes even further down. That means the current goes even further up. And so what it would mean is that every time you turn on a light bulb, it would, right in front of your eyes, destruct itself. That's not happening. It's the other way around. So in a way, it's fortunate that the resistance goes up when the light bulbs get hot. All right. Let's now be a little bit more quantitative on some networks of resistors. And we'll have you do a few problems like that, whereby we just will assume, naively, that Ohm's law holds. In other words, we will always assume that the values for the resistances that we give you will not change. So we will assume that the heat that is produced will not play any important role. So we will just use Ohm's law for now, and if you can't use it, we will be very specific about that. So suppose I have here, between point A and point B, suppose I have two resistors, R1 and R2. And suppose I apply a potential difference between A and B, let this be plus and this be minus, and the potential difference is V. And you know V, this is known, I give you V, I give you this resistance, and I give you that one. So I could ask you now, what is the current that is going to flow? I could also ask you then, what is the potential difference over this resistor alone, which I will call V1, and what is the potential difference over the second resistor, which I call V2? Very straightforward question. Well, you apply now Ohm's law, and so between A and B there are two resistors in series. So the current has to go through both. And so the potential difference V in Ohm's law is now the total current times R1 plus R2. Suppose these two resistors were the same. They had the same length, same cross-sectional area. If you put two in series, you have twice the length. Well, so twice the length, remember, resistance is linearly proportional with the length of a wire. And so you add them up. So now you know R1 and you know R2, you know V, so you already know the current. Very simple. You can also apply Ohm's law, as long as it holds, for this resistor alone. So then you get that V1 equals I times R1. So now you have the voltage over this resistor. And of course V2 must be the current I times R2. And so you have solved your problem. All the questions that I asked you, you have the answers to. We could now have a slightly different problem, whereby point A is here, but now we have a resistor here, which is R1, and we have here R2. And this is point B, and this is R2. And the potential difference is V, that is again given. And now I could ask you, what now is the current that will flow here? And then I can also ask you, what is the current that would go through resistor 1, and what is the current that could go through resistor 2? And I would allow you to use Ohm's law. So now you say, aha, the potential difference from A to B going this route, that potential difference is V, that's a given. So V must now be I1 times R1. That's Ohm's law for this upper branch. But of course you can also go the lower branch. So the same V is also I2 times R2. But whatever current comes in here must split up between these two. Think of it as water. You cannot get rid of charges. The number of charges per second that flow into this juncture continue on. And so I, the total current, is I1 plus I2. And so now, you see, you have all the ingredients that you need to solve for the current I, for the current I1, and for the current I2. And you can turn this into an industry. You can make extremely complicated networks of resistors. And if you're in course 6, you should love it. I don't like it at all. So you don't have to worry about it. You're not going to get very complicated resistor networks from me. But in course 6, you're going to see a lot of them. They're going to throw them, stuff them down your throat. The conductivity